Okay, now we're in the second video, second part of 3 of this lecture, in which we are going to talk about where to put the electron and how this thing actually leads you to something called band theory. Now, in solids, what you have is something that is called the tight binding approximation. So you assume that you have a huge molecular orbital. So all your atoms interacting, since they have this very steady, very repeatable interaction, they interact with each other so much that you can consider that the molecular orbital will end up all over the material. So it's a huge, huge, huge level of bonding, and you delocalize the electrons all over these huge molecular orbitals that go throughout the structure. So it's very difficult to visualize when you put it like that, but if we build it up, it's going to be possibly a bit more understanding. So imagine that you have one single atom with one s orbital. So one atom, one s orbital. Fine. One s orbital, one electron, call it a day. Yeah, by itself is going to be isolated. So the moment you put 2 is the moment where, in like basic approach to chemistry, you will just put the electrons in between. But now that we know that you can make a molecular orbital, you could just say, okay, I have the bonding molecular orbital and the anti-bonding molecular orbital, because with 2 interacting atomic orbitals, you end up with 2 molecular orbitals, one bonding, one anti-bonding. So one down, one up, in comparison to the energy of the first one in the vacuum. So in comparison to this one, you end up splitting one down, one up. Now, if you add a third atom next to the side, 3 atomic orbitals, 3 molecular orbitals. So one bonding, one anti-bonding, very much high in energy, and one non-bonding in between that ends up being like a bit at the same energy as it was before. We can add the fourth one. So at this point you have 4 atomic orbitals, 4 molecular orbitals. They end up being 2 bonding, 2 anti-bonding, and you start to see this sort of trend in which you end up with a space in between. So if you keep adding atoms and atoms and atoms, you will end up with 6 atoms, meaning 6 bonding, 6 anti-bonding, or 11, 12, 25, 55, 120 bonding, and 120 anti-bonding. The issue is that the more you keep adding them, the fewer space can you possibly have between them. So if you add an infinite amount of atoms, like n atoms with n s orbitals, you will end up with n molecular orbitals, but there is a limited amount of split that you can have. They cannot jump in energy further away because they are just atoms. So all the series of bonding, anti-bonding, bonding, anti-bonding, bonding, anti-bonding will fill up the energy space so much that you can consider that when you just have them interacting, there is a whole band of energy that you could possibly just occupy. Just because you're there, you can sit yourself into this space. So if you are any electron belonging to any of these atoms, there will be an energy level over here that you can just occupy by nature of being part of the structure. Now, this we've done with s orbitals, but there is no reason not to be able to do it for the p orbitals. So you have all the interacting lowest level bonding, so you have all the lowest level over here, which is completely bonding, is the lowest possible energy state that you can achieve. You have the top one here that is the highest level energy level that you can achieve, so it's completely anti-bonding in character. But in between you have any variation of this degree, but they are continuous in energy. No reason not to be able to do this for the p orbitals. So sp in energy, so above a band of s orbitals, you will end up just with a band of p orbitals. They might be occupied, unoccupied, whatever you want, but the band is there because you have a series of atoms interacting with each other. So whereas the s and the p by themselves, they will be over here, in a solid you end up with a whole band of possible energy by nature of the fact that they are interacting with each other. Depending on how these atoms are arranged and depending on what is their energy arrangement of the p and the s band, the s, the p, the d, the f, whatever, you will have a different spacing between these bands because that's atom dependent. There might be, as it is here, as is shown there, a band of energy, so a sequence of energies in which there is no orbital, no molecular orbital that can actually land in there, so there is just no energy allowed and there is a gap in between. It might or might not form. Now this is still maybe a bit theoretical, but this is the idea. Like you end up with a series of possible energy spreads that you can occupy. If we try to put it a bit more in a specific example, imagine the electronic structure of an atom like lithium. So lithium has the electronic configuration of helium by itself, so it's like helium, but you add a 2s orbital with one electron inside, and if you go higher in energy, the 2p orbital is going to be completely unoccupied because there is no electron there. Now, in 1 milligram of lithium, you have roughly 10 to the 20 atoms. If all the 10 to the 20 atoms have this type of electron configuration, it means that you have 10 to the 20 valence electrons. If you make the sequence of the 2s orbitals, there will be like 1 per 10 to the 20 atoms, and these are molecular orbitals, because if you put 10 to the 20 2s 2s orbitals, you expect 10 to the 20 molecular orbitals, of which occupied will be half of the 10 to the 20. Why? Because the Pauli principle is still a thing. When you go into the 2p, so once you make a whole solid of a sequence of lithium atom, the 2p, they will all interact with each other. There will be 3 per 10 to the 20. Why 3? Because you have 3 p orbitals per every energy level. The 10 to the 20 molecular orbitals, all of them will be empty. There should be no electron able to occupy them to begin with. So when we put it in sequence, so this is your isolated lithium atom. If you try to put 2 of them, then you end up with 2 s orbital, and then you end up with 6 p orbitals, because it's 3 and 3 of the other atom, so 3 atomic orbitals, 6 molecular orbital in between. When you go into lithium 3 of the s level, and then 9 of the p level, and you can see already here that it starts to get a bit more crammed in between. If you put 25 lithium atoms, which is already very tiny, it's not that many, you end up with 25 all arranged together and 75 all arranged on top. So since the energy spread is limited, so this, how high this band is limited, here is very, very, very cramped. So you start to see that you're actually filling up a sequence of energies that are very close to each other. Now, if you actually push this up, because we want 1 milligram of this sample, then you need 10 to the 20 atoms, which makes so that at some point these two bands will cross over. So you have 3 10 to the 20 two 2p orbitals in molecular form, and then you have 10 to the 20 molecular orbitals of the s band. You fill half of them, you end up having a huge series of level. They just go all the way up. This part is full, this part is empty, doesn't matter. The orbitals are overlapping. The last one in this sequence that you have occupied, you could call the highest occupied molecular orbital, also known as the HOMO. But above this, there is still a huge sequence of possible places to occupy for your electrons, because they're all crammed together and it's impossible to distinguish where the energy of one molecular orbital finishes and the next one begins. They're just one equivalent to each other. Now, when you are at 0 Kelvin, this is the most basic energy state. There is no additional energy that you give to your system. Is 0 Kelvin, nothing, nothing, nothing. This is called the ground state. You cannot go any lower. This is the base state of your material, the same one that we can derive theoretically as we were doing before, just like you arrange your energies, you arrange your electrons. That would be the 0 Kelvin configuration, the ground state of your material, which will mean that you end up with all your electrons crammed down and this highest occupied molecular orbital, the HOMO level. At this level, when you are at 0 Kelvin, this level of energy that you can see over here is called the Fermi level. The Fermi level is the last point you occupy with electrons at 0 Kelvin. So that's your HOMO level for 0 Kelvin. Anything that is above the Fermi level at 0 Kelvin is completely empty. Anything that is below is completely full. And that's it, and you call it. Now, you have a tiny issue, which is, as you might very well know, the temperature of 0 Kelvin is A, not the usual, B, not even really achievable. So when you are in a state of having thermal energy, so something extra to give to your system at any temperature that is below 0 Kelvin, some electrons might find themselves with enough energy to actually jump into one of the unoccupied state. Why? Because they're just there. Why should they not? It's easy, right? This makes possible the mobility that you have, because an electron can only move if there are empty energy states around it, which is not the case if all the states are occupied, like in below the Fermi level at 0 Kelvin. Is absolutely the state when you are above 0 Kelvin, and there are a series of unoccupied levels that are just within reach to jump. Now, the population that you end up having, so how many electrons are actually distributed in which sequence above the Fermi level, is something that follows the Fermi-Dirac distribution. So this is this type of step function, more or less. Why do we call it the Fermi-Dirac? Because this way in which this thing is defined actually takes into account not only like the Boltzmann population, which is the thing that will just go with this kT divided by something. It takes into account the fact that you need to have the Pauli principle of pairing the electrons together if you can. This thing gives you basically the probability to find an electron above a certain level. Now, if we were to be at 0 Kelvin, the probability will be 1 up to the Fermi level. They're all here. When you go above the Fermi level at 0 Kelvin, there is nothing. So either you have 1 or you have 0. This thing is like this quantity mu is the chemical potential, and the kT gives you the thermal energy. So this becomes a modifier to your probability, which makes so that you start to bend the shape of your step function. So there is a tiny possibility that there will be something above the Fermi level, and a tiny possibility that something below the Fermi level will shift and go off. So the more this ratio goes to a different level, the higher this mix will become. So if you manage to land into this level, then you will end up with all this part above here empty, and all potentially empty, and all of this stuff potentially occupied. So this thing now, the more you go, the more it resembles a Boltzmann type of distribution. So exponentially, with increased energy, you decay down. So the higher the temperature, the longer the tail. So at relatively low temperature, the tail here is very tiny. The higher you increase the temperature, the more the tail shifts and give you more and more and more energy states in which your electrons will just free to go by thermal energy. Bam! That's the chemical potential. Now, this makes so that you can have a metallic type of conductivity. Metallic type of conductivity means that the electrons above the Fermi level, like near the Fermi level, are mobile. So since there are unoccupied level easily within reach with any thermal energy that is above 0 Kelvin, you can just occupy up there and conduct electricity, which is the reason why this thing is called the valence band, but this one is called the conduction band. This band theory arrangement means that this is the description of all the molecular orbitals occupying the whole structure. You might have heard in high school even about a metal has a sea of electrons in which the electrons can be delocalized all over the structure. Why? Because the way you describe the bonding in a structure that is interacting is by counting all the atomic atoms of all of these things all together, make a band out of them. Most of the lower levels will be occupied with thermal energy above 0 Kelvin. You will find yourself with an unoccupied level that spans of energy, that spans the whole material, in which your electrons can actually twinkle around and move around. So this is the reason why you can have a sea of electrons, because there is something easily within reach with a tiny bit of temperature. Your electron can just zing and move it. So metallic conductivity is inevitably the highest type of conductivity. So the material that conducts the best is always a metal, because there is always somewhere in which you can just go with the electron and give it a path to go around. On the other hand, depending on the characteristic of your material, you might have a valence band and a conduction band that are separated by that infamous part of energies in which you have no possible molecular orbitals. This thing is called the band gap. So you have two bands, but there is a gap in between. If this gap is way too big, there is no way you can jump from one to the other. This is the case usually with diamond and with a lot of material that end up being covalent like this. So diamond in itself has a face center cubic structure. So you can see that this cube has the corners occupied and the face in between. And inside, all of the atoms find themselves with 4 possible neighbors, all over the place, over and over and over and over again in the 3D space. Now, if you think about it, this leads to your central atom with 4, like if you think about the hybridization of this thing, so S and P hybridize, make 4 sp3 hybrids. So this thing in the center has 4 sp3 hybrids, each with 1 electron. And then you have the corners. For every corner atoms, you are trying to bond the central one with a single sp3 hybrid. So you have 4 corners, 4 sp3. Now you make 4 down, 4 molecular orbitals down, 4 molecular orbitals up, The down are completely empty because you want to pair them, and the up, the anti-bonding, are completely, this is completely full, and this one up here is completely empty. The more you bond, so the more atoms you put in this arrangement with this rule and this trick, the more this gap in between, instead of filling up, given the differences in energy that you have between your materials and between your atoms, the band grows. So you have a lot of the full down here, a lot of the empty up here, but the space that is in between grows. There are no energy states available for you to populate with electrons. Doesn't matter how much energy you put, thermally speaking, it's just not there. This is just something that you cannot do. And there's a big band gap, and usually with insulators, in which you cannot conduct electricity, it's above 4 electron volt. Electron volt being the energy to move 1 electron with 1 volt of potential. It's a common energy unit used in solid state. Now you have the intermediate option, in which there is indeed a gap, but this gap can actually be bridged. How? With enough thermal energy. So the semiconductors are the intermediate behavior between the metallic conductivity and the insulating conductivity. They still have a space between the two bands, a band gap, in which there are no available energy levels. At 0 Kelvin, this thing is an insulator. You cannot move the electrons around. If you give enough thermal energy to your semiconductor, how much is enough? How big is the gap? Depends, right? You can bridge the gap, so there are some electrons that will find themselves with enough energy to actually go and occupy some of these unoccupied levels that become partially occupied, and then they can zigzag through the structure and conduct. The smaller the gap, the easier it is to bridge the energy. So there are some mobile electrons in semiconductors. Those little percentage of mobile electrons are the only one that can conduct. So the conduction in a semiconductor is thermally activated, and this is the case, for instance, for something like a silicon wafer. Then you have one more type of potential conductivity, which is a material like this, which you should remember what type of material takes this arrangement. Think about it. Now the question here is is this thing a conductor or an insulator? We show the band as big blocks, big rectangles, but this is not strictly accurate. You can actually have a distribution in space depending on where they are pointing, and they don't need to be blocks. This means that you can have still a distribution in energy, but if the band is changing shape, you could have a situation like this, in which it's not like all the positions in space are equally energetic. If you are in this position, you have a huge gap, and instead with certain directionality, certain atoms involved in a certain bonding, you end up having a single point of contact, and that's what you will call a semi-metal. So the two bands touch exactly at the Fermi level, and this is a significant contribution to the conductivity, because in this orientation, with these levels involved, you can conduct. The other ones do not. So this is exactly what happens in graphene. So in graphene, you have just one plane of graphite, and you have this type of conductivity, so you can conduct in the plane on the ground of this business. But then between different layers of graphite, the situation is different, the distances are different, the bonding arrangement is different, and the quality of the bonds is different. So when you try to conduct between the planes of graphite, then you find yourself with a completely different business. The conductivity is order of magnitude lower, in Siemens to the centimeters. That's usually the measure of conductivity. So you can have a material that, given the bonding arrangement and the atoms involved and the complexity that arises from them, has a band structure that is way more intricate than this overlaps with this or this. There is a huge space and nothing in between. And you can have different behaviors depending on where in the structure are you looking into doing stuff. Yeah. So, summary of the type of conductivity. Metallic conductivity, any electron that is close to the Fermi level, only those one, you don't conduct from this one at the bottom to this one at the top, at close to the Fermi level, any energy above 0 Kelvin makes it conduct electricity. This is usually the best conducting material, best meaning that we are in the order of magnitude of 10 to the 6 Siemens to centimeter. In insulators, you have such a huge gap in which there are no energies available for your electrons to go around that there is no way to bridge it, no matter how much temperature you put inside. You cannot bridge the gap. Your conductivity is in the order of 10 to the minus 12 Siemens to the centimeter, case of diamond, for instance. And then you have intermediate cases in which the conduction is thermally activated. You can jump a little, is usually around 10 to the minus 2, so still orders of magnitude of difference with the metals, but it can be thermally activated and thermally tweaked. Now, take-home message for the band. Here, when you have this gap over here and everything is filled up, this is the highest occupied molecular orbital at 0 Kelvin. This is the lowest unoccupied molecular orbital, so LUMO, at 0 Kelvin. If you tweak the possibility of acquiring these energies, it changes, and you can actually do something because you have the possibility of going around. Now, when we talk about the possibility of going around, where is the electron going in this whole business? The electron is going nowhere. It's not moving away from the structure. A conduction band and an ionization energy are two different concepts. The electron is not leaving the structure. The electron is just going into a different energy space. So it's not jumping off the structure, still there. Just that it would be a bit like you're on a highway, right? If there is a line in the highway that is completely empty and you're trying to take over and go past all the other cars that are queuing, that's your conduction band, right? You're not leaving the highway, you're not yeeting yourself out of the highway and into the wildness, into the countryside around the highway. You're still on the highway, just in a slightly different arrangement in space, which in this case is an energy space that allows you to go to a completely different regimes. So in given quantum mechanics and all this black magic arrangement, you could be in the same exact spot in space. If you're in two different energy places, you do not see each other, and you can just move as if you're unconcerned that the other electron is there. So band behavior can only be there because you have moles and moles and moles and moles of atoms interacting with each other. You have so many of them that they make this type of distribution, like completely continuous in space. This is a type of property and a type of bonding that only ever exists in solid. But as you can see, is the only reason you have a series of properties that are actually reflecting what you know experimentally. Like, you are used to the fact that copper will conduct electricity. Why? Because of this. If you were to try to analyze this from the point of view of just like materials, like, or just bonds, ionic bonds, covalent bonds, it won't work. You need to go into the bands. And given these behaviors that we discussed, they are all thermally activated. The conductivity as a property of the material depends on how many carriers do you have, so how much stuff is there to conduct electricity, what is the charge, and what is the mobility. So if it's electrons, how many electrons of charge minus do you have that are actually able to zigzag through your structure. due to thermal vibrations, it's not like you can increase this conductivity at your leisure, just go to 2000 degrees and everything will conduct. You actually have some tricky behaviors. So with increasing temperatures, the conductivity actually decreases in metal. So a metal that is already really conducting, when you go to a very high temperature, becomes less conducting. Why? Because of the crowding of the highway. If there are a lot of cars in the takeover line of the highway, you are still crammed, right? Same effect. Increases in insulators, because if you push a bit, something statistically speaking might be able to vaguely jump. So increases a tiny bit, not much in insulators. But in semiconductors, then it's a huge business, because if you increase the temperature, semiconductors just go, you call it a day. And you can see here that you actually split in two possible behaviors that start at two different conductivities in a lower temperature regime. So in intrinsic semiconductivity, the carriers that you want are just activated by temperature. They can only jump because you make them jump with temperature. In extrinsic semiconductivity, that you can see starts higher, you already have some carriers in the structure that are mobile. Now, this concept is something that we are going to explore more in the final part of this lecture in the third video.